Okay, in this video I'm going to talk about Brocard points of a triangle. So let's say that we have an arbitrary triangle, and a point P is called the first Brocard point if we connect it to the vertices of the triangle, and these angles so this angle is equal to this angle and is equal to this angle. So if these three angles are equal to each other, then this point is called the first Brocard point of this triangle. And the second Brocard point, so this is the first Brocard point, and Brocard point, and the second one is constructed similarly, but we take the angles in the other direction. So this angle is equal to this angle and is equal to this angle. So this point Q is called the second Brocard point of this triangle. So this is kind of the definition, but the theorem is basically that such points exist and they are unique. So let's write it as a theorem. Theorem 1. So the first for every triangle, for every triangle there exists a unique first Brocard point. First Brocard point, and theorem 2 is basically the same for the second Brocard point. So for every triangle there exists a unique second Brocard point, meaning that the point with this property that these angles are equal to each other, and for the first Brocard point that these three angles are equal to each other. It's important to note that these triangles are not just equal to some fixed angle, but to any angle. So if a point P is such that these triangles are equal between each other, it doesn't matter what is the value of this angle, then this is called the first Brocard point. So the theorem says that such point exists, that it's unique for any triangle. So so the theorem 2 is clearly because of the symmetry. Theorem 2 is basically it follows from theorem 1. If we basically rename the triangle, instead of considering the triangle ABC, so ABC, we consider ACB like rename it in other, like in the opposite direction. Then the first Brocard point of ABC would be the second Brocard point of ACB, and vice versa. So they're clearly symmetric to each other. So like if we prove theorem 1, theorem 2 is like it follows from theorem 1. So yeah, so for that reason we will prove only theorem 1. So for the first Brocard point, so we do the following constructs. Yeah, so this is the proof of theorem 1. So we have an arbitrary triangle, and yeah, so construct so this is A, B, C. So construct perpendicular bisector of the segment AC. So we take midpoint and construct the perpendicular from the midpoint. Right, and now we construct a perpendicular to the line AB from the point A. So such line that is perpendicular to AB and passes through A. Right, we can always construct this. So we take the intersection of these two lines, and so we notice what is this point. So because it lies on the perpendicular bisector of AC, it is at the same distance from A and C, right? So these two segments are equal to each other, and if we consider a circle with this center, so like let's denote this point by I don't know, like let's denote X. So we consider a circle, like a circle with center X and radius AX, right? So we consider a circle with center X and radius AX. So then, so something like this. So, well, we don't need this, but just so it clearly passes through both points A and C, right? So because it has radius AX, but X is at the same distance from A and C, right? So it passes also through C. But now also it is tangent, so this circle is tangent to the line AB. So this circle, so like let's denote it by omega. Or I guess like omega, let's denote it omega B. So this omega B is tangent to the line AB, and this is because of this perpendicular, because of this right angle, because the radius like the line perpendicular to the radius is a tangent to a circle. So if this line AB, it passes through a point on the circle A, and it is perpendicular to the radius at this point. Therefore, it is a tangent. It's a well-known property. So therefore, yeah. So now we construct a similar circle for for the line. So let's remove this word proof. Similar circle for we construct perpendicular here, right angle here, and the perpendicular bisector of the segment AB, right? So, and we construct similar, so let's denote this by Y, and we construct a circle with center Y that passes passes through A and B. Such circle. So then it is also, so similarly it is tangent to BC. So like denote this circle by omega C. So omega C is tangent to BC. Now we consider the point of intersection, the intersection point of these two circles denoted by P. So clearly there is a point of intersection because because point A is the common point of these two circles, so they do intersect. So the second point of intersection, unless they are tangent to each other, in which case we just denote P to be A. So the second point of intersection we denoted by P between these two circles, so now we observe that this angle, so the angle BAP is equal to this angle, to the angle PCA, because because these two angles subtend the same arc AP in the circle omega B, right? So the angle PCA, so this is an inscribed angle subtending this arc AP, and the angle BAP, it's it's kind of a limit case of an inscribed angle. It's the angle between a tangent and the chord, and there is a well-known property that the angle between a tangent and the chord is equal to all the inscribed angles subtending the same arc. Like I proved it in one of the previous videos. So these two angles are equal to each other. Now if we consider the third segment BP, then this angle would be equal to this angle. So angle BAP, so BAP, this angle is equal to the angle CBP, this one, for the same reason, because they subtend the same arc BP now in the circle omega C, right? So the angle BAP now is an inscribed angle in this second circle omega C, and the angle CBP is the angle between a chord and a tangent. So they are equal to each other, and therefore all three angles are equal to each other. So all three angles are equal to each other, and this is exactly what we need for the first Brocard point. So this is exactly the picture that we get. So we explicitly showed how to construct this point P. So Now observe that we can actually construct a third circle. So like if we consider the circumcircle of the triangle BPC, right? So this circle, then it must be tangent to the line AC, because these two angles are equal to each other. So so it must be a tangent. Yeah, there's something like this. Yeah, so this is the first Brocard point, and like as I already mentioned, the second Brocard point is it follows from the first Brocard point. The proof of the theorem for the second Brocard point follows from the first theorem. Yeah, so this concludes the proof.